We will present a submission on learning actions for drift-free navigation in highly dynamic scenes. The problem of active navigation stems from the requirement of exploration and exploitation of unseen environments by some sort of a mobile robot. In an autonomous system, the robot localizes itself and maps its surroundings. It then proceeds to pick goal points to reach depending on the task. In active navigation, the robot's navigation stack should come up with trajectories that solve for both goal reaching and drift minimization simultaneously. This results in trajectories that are perception and drift aware as well as capable of reaching the goal. Ours is the first work to tackle the problem of drift minimized navigation with LiDAR as the primary sensory modality. We use reinforcement learning, specifically proximal policy optimization or PPO for short, in order to learn actions that can minimize drift. For modeling a PPO, we delicately define a reward explained in the following slides. The waypoint generated by our RL model are then traversed using a Stanley controller that solves the path tracking problem. We will now discuss the complete pipeline of our system. A scene in Kala simulator containing an ego vehicle along with traffic vehicles is the required input scene. We send the data from the ego car's perception system, which is a 3D LiDAR, to the LiDAR odometry and mapping algorithm, or LOM for short, which performs SLAM in the LiDAR setting and outputs an odometry. We filter dynamic obstacles from the scene at this stage and obtain the state of the RL model. This state contains the ego's pose, the traffic car's pose, the location of the centroid of features around the ego vehicle, etc. Our RL model, whose reward is shaped to achieve behaviors such as moving towards features and avoiding traffic, is trained on this data. This model then outputs actions for the ego car to execute, which are discrete waypoints. A cubic spleen is fit on these discrete waypoints for interpolation, and a Stanley controller is used to perform path tracking on the interpolated trajectory. The first module of a system is the perception and dynamic obstacle filtering module. As mentioned previously, we use LiDAR odometry and mapping, or LOM, for state estimation and localization. We remove dynamic obstacles in the scene through Kala's inbuilt point cloud filtering API. The second module is the waypoint generator, in our case the PPO model. The model outputs discrete waypoints for the ego vehicle to traverse. During inference time, the model is unrolled for n steps to obtain the desired waypoints. Usually, we set the n to be 10 during our testing. Therefore, in a third module, we interpolate the waypoint by fitting a cubic spline on these 10 generated waypoints, thereby obtaining a smooth trajectory for the ego to traverse. Our fourth and final module is a path tracker, in our case, a simple Stanley controller. This controller is responsible to track the interpolated path obtained from the third module. We will now discuss the most important module of our system, the waypoint generation, which is modeled as an RL problem. Here, we briefly describe the notation used in this paper. XE and YE represent the X and Y coordinates of the ego vehicle. YC represents the centroid of the edge features present in the current scene. This value is clipped between -1 to 1 for numeric processing. Edge L and Edge R represent the lateral road boundaries, XTRI, and YTRI represents the X and Y coordinates of the ith traffic vehicle. TRPI is a boolean representing the presence of the ith traffic vehicle in the scene, and VTRI is the velocity of the ith traffic vehicle. The RL agent has a discrete set of actions that it can choose from, namely capital A. Each action, small a, in capital A represents the waypoint in the next time step for the vehicle in the vehicle's frame of reference. This action A is defined as a tuple containing AX and AY. AX is chosen from the set 1, 2, 3, 4 and 5, and AY is chosen from the set -2, -1, 0, 1 and 2. These actions were selected in such a way that the ego vehicle can execute a diverse range of motions, from slow straight moving to fast turning motions. The reward function is designed to capture both the motion objectives as well as the perception objectives of a system. In order to do so, we split the reward into three components: the goal reaching reward G, the feature proximity reward F, and the traffic proximity reward T. They are combined into a complete reward R as shown. Here, P is the boolean representing the summation of logical OR statements that represent the presence of traffic vehicles inside a defined proximity radius. The goal reaching reward primarily rewards the ego vehicle for its successful motion towards the goal. This reward also performs a few checks for the ego vehicle's motions, such as the vehicle must be outside the road boundaries defined previously as edge L and edge R. Secondly, if the vehicle collides with the traffic vehicle, the reward triggers the episode termination. The feature reward F is responsible to ensure the ego vehicle successfully moves towards the feature-rich regions. This is because feature-rich regions lead to better scan matching in LOM. LOM algorithm provides a smoothness measure that can be used to determine the distribution of feature-rich regions. Here, YC represents the centroid of these features. We will now explain the math behind the feature proximity reward in detail. First of all, the reward is split into two terms controlled by constants K1 and K2. The first term is said to be triggered if there are features on only either side of the road, and the second term is said to be triggered if there are features on both sides of the road. In the first term, YC is raised to a high odd power and multiplied with normalized YE. This ensures that the reward is high when both ego and feature-rich regions are on the same side and vice versa. The second term is the same YC raised to a high odd power subtracted by -1 and multiplied by the lateral action AY. For the second term, it prevents unnecessary lateral motion with no particular side when no particular side is decisively feature-rich. The traffic reward T is responsible to ensure that the ego carefully avoids dynamic traffic vehicles in its vicinity. This is because LOM estimates are adversely affected in the presence of traffic even when we filter out points coming from them as shown in qualitative results. To design this reward, we first define a traffic proximity region, defined as an equilibrium distance between the ego and the IF traffic car. This reward is split into two terms controlled by constants K3 and K4. The first term is simply the difference between the action along the x-axis, which is usually along the length of the road, and velocity of the ith traffic vehicle. The second term is the difference in the absolute differences of y coordinate of the ego vehicle and the ith traffic car in the current and previous iteration. Both of these terms return a positive reward when the distance between the ego and the traffic is increasing. We will now discuss the results of our experiments. In this figure, we show our LADFN system significantly reduces drift compared to competing benchmarks on a variety of color scenes. LADFN is shown in green and orange bars that represent filtering of dynamic vehicles enabled and disabled respectively. Similarly, the competing benchmark, a standard Stanley controller, is shown in blue and purple bars. Firstly, we want to show that LADFN leads to lower average drift than the benchmark. This is clearly shown in the first column, where LADFN reduces Stanley's drift by at least 1.4x. In the second column, we seek to provide a framework for analyzing the performance of the goal-reaching task by observing the final transitional offset or drift. Here, LADFN consistently outperforms Stanley controller by at least 1.63x. The third column shows the rotational errors, specifically yaw, and it shows that LADFN significantly reduces them as well. We will now look at the behaviors learned by our RL model. In the first scenario, the ego vehicle starts alongside two traffic cars on both sides. The surrounding scene contains building on the road's left side and nearly zero featured regions on the road's right side. In order to move closer towards the building on the left, the ego performs a quick maneuver, initially towards the left, which brings it into the position to drive down the left lane of the road. It then proceeds to move straight down the left lane, thereby keeping the features from the buildings close to itself, reducing the overall localization errors. This scenario is set up much like behavior 1, with the exception that the traffic cars are now stacked one after the other on the left lane. One of the traffic vehicles is in the front of Ego's lateral wipe position, so this time the Ego cannot make a quick turn into the left lane directly. It should judicially seek to overtake the traffic vehicles in front of it and on the left lane, which it does when the first 10 waypoints are unrolled through our RL model's inference. During the next step of inference, the car simply moves straight down the left lane on the road to keep features from the buildings in proximity. The scenario represents a static scene in which there are no traffic cars present around the Ego vehicle. Here, the right side of the road is feature rich. The car spawns on the leftmost lane of the road. When the first 10 waypoints are unrolled through the inference, the Ego car is seen to immediately move towards the right lane. After successfully making the turn, the Ego car moves straight down the right lane to keep features from the buildings in its proximity. Notice there is no unnecessary speed up in this case. Thank you.